All right, welcome everybody to Lecture 6 of Statistical Methods in Psychology. Now, last time in Lecture 5, we learned how to translate research questions into statistical questions about some population mean mu. So anytime we had a research question in context, we essentially stripped that context away and turned it into a purely statistical question about mu. And we developed two methods for answering these statistical questions. The two approaches were this. The first one was an estimation approach, where we learned how to estimate a 95% confidence interval for mu, so that we could say things like, we are 95% confident that mu is between some number x and some number y. And so that's how we interpreted our questions about mu in that light. The other method that we did was hypothesis testing. And that method works by defining competing models for mu. So these are statistical hypotheses that we labeled H0 and H1, where H0 was the null hypothesis and H1 was the alternative hypothesis. And what we did was we computed the probability of observing our sample mean x bar if the null hypothesis is true. And the basic idea, which we will review again today, is that if that probability is small, the null is not a good model for our observed data, so we end up rejecting it in favor of the alternative. At this point, I want to point out a technical note that's going to give us some problem very soon. You may have noticed in our previous examples that every example we did included somewhere in the problem the population standard deviation sigma. Every problem that we have done for these kinds of problems you have been given a value for sigma. So the natural question then is, what happens if we're not given sigma? So here's an example where this happens. Suppose we have a population that has a mean of 23. A sample of n equals 4 is given an experimental treatment, and these scores were 20, 22, 22, and 20. The research question that I want to ask is, does the treatment result in a significantly lower score? Now, this will look very similar to the types of questions that we asked in the last lectures, but there's one thing missing. We are not given sigma. Nowhere in this problem are we told that the population has a specific standard deviation. So what can we do? Well, it turns out that we need a new technique. So what is this technique? Well, let's try to figure out, how do we get a value for sigma? We're certainly going to need one, because if you remember from last week, we had to have sigma when we computed our z-scores. It's part of the z-score formula. So how do we get it? Well, I think the obvious thing to try first is that maybe we just estimate it from the observed data. Now, you might remember from back earlier in the course that we can compute the standard deviation of a set of data by simply taking the sum of the squared deviations from the mean and then dividing by n. I've written this as 1 over n times that sum of squares. And then you take the square root of all of it to get it back on the same scale. So we can certainly do that. That's not too hard. But the problem with doing that is that S tends to be too small. What I mean by that is that when you compute this number right here, this thing that we have been doing all semester as the standard deviation of a set of points, that computation systematically underestimates the true value of sigma. It's called a biased estimator. So what we need to do, since this is a problem, is we need to correct that formula to fix the bias. So how do we do that? Well, it turns out to be really cool. Here's how we fix it. What we do is we introduce a slightly different formula. We're going to call it sigma hat. So you see that little symbol that's sitting, the little caret symbol that's sitting above the sigma? That is a hat. We call that sigma hat, and the hat indicates that it's an estimator of the value of sigma. It's not this unknown population parameter itself, it's rather an estimator from data. And what we do is we essentially do the same thing as above, right? We take this sum of squared deviations, that's what this part is, but instead of dividing by n and finding the average of those, we divide by n minus 1. Okay? just slightly different. An easier way to remember this is we take the square root of the sum of squares divided by n minus 1. Now, what does this do? Well, if you think about this in terms of the numbers involved, consider the original value that we looked at up here, where you divide by n. Okay? What would happen if you divided instead by n minus 1? Well, n minus 1 is a smaller number. When you divide by a smaller number, the answer becomes bigger. So what's happening with this estimator is you are fixing the underestimation by simply inflating it by a certain factor. And it turns out, and I'm not going to get into the mathematics here, but it turns out that that's all you need to do to fix the bias in computing or estimating the standard deviation. Okay, fine. All right, so we can do that. We'll do that in our example here in just a second. But there's another problem that comes from this. The distribution of these z-scores that we would compute, now I've put quotation marks around the z-score because strictly speaking, this is not the same formula that we used last week. Why? Because we're using sigma hat. We're using an estimator, not the actual value of sigma. That distribution no longer turns out to be a normal distribution. But in fact, it's something else entirely. It's a totally new type of distribution for us. And so what this does is it throws out the technique that we did last week where we computed this z-score and then found the probability with our normal distribution calculator. Remember this thing? Turns out we can't use that because the distribution of these scores is not normal. It's something else entirely. So how do we fix that? That's what we're doing this week. What it turns out to be is something called the t-distribution. And this is a new, very important distribution for us. It's been around for a long time. The details, the mathematical details of this distribution were actually worked out by several people, and what we do now is an amalgamation of different approaches. But essentially, this goes back to a paper by Gossett in 1908. Interesting little bit of tidbit on this. This was published in the journal Biometrica, which of course is still around today. It was written under a pseudonym, Student, and sometimes it's called the Student's t-test. Some people think it's because we teach it to students. No, Gossett worked for Guinness Brewery, and so he could not publish under his name, but rather Guinness made him publish under the name Student. There's a nice history of this paper given in Zabel 2008 in the Journal of the American Statistical Association, so you can read all about the history of that. The thing about this distribution that's new for us is that the shape of the distribution, remember I told you it's not normal anymore, the shape of the distribution depends on the sample size. That parameter that it depends on we call degrees of freedom, and the degrees of freedom, which we denote df, is found by taking the sample size minus 1. Okay? And that's how we're going to choose the correct distribution to use when we get to computing probabilities, is we're going to have to specify this degrees of freedom. Now, what do I mean by the shape depends on the sample size? Well, let me give you a really bad drawing. Okay, so the basic idea is this. The smaller the sample size, the fatter the tails of the distribution. So consider these two curves that I've plotted down here. These are terrible renditions, I'll give you that, but they're at least sketches that indicate what's going on. Consider the blue curve first. That's this one here. That is the t-distribution, or at least my rendition of the t-distribution, for a sample size of 25. Okay. Consider next the red curve, which is this one right here. That is the t-distribution that results when the sample size is only 5, so it's a smaller sample size. And what you'll notice is that the tail regions are much thicker. We call that fatter tails out here for the red curve compared to the blue curve. So what that's going to do is it's going to force us to make sure we're super careful when we start calculating probabilities. Because the shape is different for every possible sample size, then we must make sure that we specify that sample size when we go to any sort of calculator to calculate our probabilities. Now, we've been calculating probabilities this semester with this app. I showed it just a little bit earlier. Remember, it's at that website, and there'll be a link in the description. But thankfully, we've already built the t-distribution into that app. So we're going to see an example of exactly how to calculate these probabilities very, very soon. So let's go back to our example, and let's talk about how we can use this notion of a t-distribution to solve it. So again, remember, we have a population with a mean of 23, a sample of 4, we've got some scores here, and we want to know, does the treatment result in a significantly lower score? Now we're going to ignore estimation for right now. We'll do that soon, but not this time. We're just going to focus on the hypothesis test. So the first thing we need to do is define a parameter. Let's let mu be the mean of the treatment population. Okay, so this is unknown, right? We don't know the population level effect, so to speak, of this treatment. So we're going to quantify it by this letter mu. Now do note that the sample mean is 21. This is our observed data. You can get that simply by taking the average of these 4 numbers. Now we'll proceed with a hypothesis test in the usual way. We'll define these 2 competing hypotheses. The null hypothesis would say that this treatment population will have the same mean as the original population. So that was given to us as 23, so the null would be mu equals 23. No difference between the treatment population and the original population. Whereas the alternative would say we're going to decrease the score from the original population. So the mu is going to be less than 23. So we set up these 2 competing hypotheses. We have some observed data. We want to know which of these hypotheses is best supported by the data, which of them best explains the data. The way that works is we assume that the null is true. So we say, let's argue, let's say that the null is true, and let's find the probability of observing our data or more extreme, that is x bar less than 23. Sorry, oops, I messed that up. We want to find the probability of observing x bar less than 21 if the null is true. Okay. So how do we do that? Well, to proceed, we would be ready to go ahead and do this probability last week, but right now we don't have a value of sigma. We don't have the population standard deviation. At this point, we've got to use our data to compute an estimate sigma hat of this population standard deviation. Now from above, let me scroll up a little bit here. Now from above, we know the formula for this is fairly easy to remember once you use it a few times. It's the square root of the sum of squares divided by n minus 1. So what we need to find is the sum of squares. We know how to do that. All right, so let's take our data, let's put it into a nice tabular format. Now first of all, the mean was 21. Let's go ahead and write that here. So let's take each data point and subtract the mean. So 20 minus 21 would be a negative 1. 22 minus 21 would be a positive 1. And then a positive 1, and then a minus 1. Those are the deviations. We want to square the deviations, so we'll take each of these and square them. They each turn out to be 1 in this case. And so this gives us an SS, a sum of squares of 1, 2, 3, 4. So now we can simply compute our estimated standard deviation by using our formula, square root of SS divided by n minus 1. We plug in the SS of 4. And then n minus 1, remember we had a sample size of 4 points, so n minus 1 is 3. Take 4 over 3 and take its square root, and we get an estimated population standard deviation of sigma hat equals 1.15. Now we can compute a t-score. This is a new thing for us, right? We would have called this a z-score before, but because of using sigma hat, it's no longer a z-score. It's a different thing. And so we call this a t-score. Everything else is the same though. So we need x bar, we need mu, we need sigma hat, and we need square root of n. So let's go ahead, I'm gonna get my notes here just to make sure that everything turns out right. Let's go ahead and plug in what we've got. So we've got an x bar of 21. What is mu? Well, remember, we don't know what mu is, except in this situation, we assumed that the null was true. And if you remember, the null is that mu equals 23. So that gives us a value to put in for mu. That's nice, works out. Okay. divided by, now we use sigma hat, which we found up here as 1.15, and we divide by the square root of 4. Now we can simplify this a little bit. The observed effect up top is a -2. The standard error at the bottom, if you take 1.15 divided by square root of 4, you get 0.575. Which then, if we put that into our calculator, we get -3.48. So our t-score is -3.48. So based on this, we can now say the probability of getting an observed sample mean less than 21 is the same as getting the probability of getting a t-score less than -3.48. Okay. So we need to go to the app, and let me undo that real quick. We need to go to the app and figure this out. So how does this work? Well, let me open up our app and reload it. So in this probability calculator, so far we've just been doing normal distribution calculations, but now we want to use this t-distribution. So we're going to go up to the distribution menu and select from these options. We have an option for t. And you'll notice the inputs change. Now it asks for degrees of freedom. So this is what I mean when you have to specify the degrees of freedom. You're specifying the sample size, essentially. Now for this problem, there were 4 data points. So the definition of degrees of freedom here is take the number of data points minus 1. So the degrees of freedom in this case will be 3. So we do that. Now we have a distribution that will calculate the probabilities correctly for us. We want to find the probability that t is less than -3.48. So we need a lower tail, and we put in -3.48. And I'm going to expand this just a little bit. That was a bad thing to do. Hang on one second. Go back in here. 3, lower tail, -3.48. There we go. So we get we get a probability of 0.02. Now there's something going on with my app here, I'll tell you that, because let me show you what I got earlier when I worked this up. Earlier I got a probability of 0.0127. I'm not entirely sure if I just did something wrong, or let's just double check this real quick. Okay, no, it all looks fine. So these things happen sometimes. Let's just put that there, go back to our lecture. So I'm going to erase this real quick, and I'm just going to put in what we had. Either way, the answer turns out to be the same. I just want to make sure and get that p-value down correctly. So from the app, we get 0.02. So what is that? That's the probability of observing our data or more extreme if the null is true. What do we do with this? Well, since that p-value, that probability is less than 0.05, less than 5%, we say that our data is rare if the null is true. Well, then that means that it's probably not the case that the null is true, because here's our data right here. It's in hand. So we say the null is no longer a plausible model of our observed data. So we reject the null in favor of H1, the alternative. Remember, that's the hypothesis that mu is less than 23. What does it mean to say mu is less than 23? That means that the treatment mean decreases. So our conclusion is that the treatment results in significantly lower scores. And that's how we do the hypothesis test. So as you can see, the logic of the hypothesis test, this so-called t-test, is the same as what we did last time. It's just that the mechanics are slightly different. We have to consider t-scores now instead of z-scores. So what's the take-home? Well, 3 things. First of all, in problems where sigma is unknown, we have to estimate it from the data. That's an important first step. And then when using this estimate, which we call sigma hat, the distribution of sample means depends on the sample size. And the result is this t-test. Everything else is exactly the same. So t-tests are when you don't know sigma. And that's it. So hopefully that kind of gets rid of some of the mystery behind a t-test. Some of you may have used t-tests before or heard of them and wondered, why are we all of a sudden doing this? Well, this is why. It all comes down to this problem right here, and the t-test is an elegant solution for that problem. So that's all for this time. Next time, we will begin working on more examples of t-tests in different situations than what we've done so far. So we'll learn how to do t-tests for problems where you've got multiple measurements, or even more importantly, measures where you've got two different groups that you want to compare. So that'll be pretty exciting, but we'll do that next time. So that's all for now, and we'll see you on the next video.